Inductance summary. Self-inductance is the EMF induced in a circuit by its own current flow and is used to define the value of the inductance proportionality constant L. The voltage drop across an inductor, and you can see here we have the EMF subscript L, is called the self-induced or back EMF and is a property of the geometry of the loop. Here's our definition of L. It's minus E sub L over di dt. L measures the resistance of a circuit to a change in current, not just the current. That's what R measures, the resistance to current. As the current changes, the circuit generates a magnetic field that creates the back EMF. And the reason it's called back, and you have the negative sign here, it opposes the applied EMF, thereby reducing the rate of current change. The inductor is a circuit element where the self-inductance is increased by multiple concentric loops of wire, and it's indicated by this symbol. And it actually kind of shows what it is, right? There's your concentric loops of wires. The inductor stores energy in its created magnetic field, and it's equal to 1/2 Li squared. And notice the similarity to the potential energy stored in a capacitor, which is 1/2 CV squared. And let's put a C there so you know it's capacitor. The unit of inductance is the Henry, where 1 Henry equals 1 Weber per amp. We have an inductor here, and the current is flowing from point A to point B. When that current is increasing through it, the electric potential difference between point A and B is positive. So VA, the voltage here, minus VB is positive. So if you wanted to put a sign on it, this would be positive, this would be a negative. There's a higher potential over here, smaller potential there. When the current is decreasing, and here's the equation, so di dt is negative, so in that case the potential difference is negative. So you would have a higher potential on the B side than the A side. When the current is constant, there is zero potential difference because di dt equals 0. An RL circuit contains a battery, resistor, and an inductor. When switch S is closed, there is initially zero current, and we show that over here on the graph. Here's time, here's current. The inductor acts to oppose the change in current. It wants to keep it at 0. Then over time, it increases as this function right here, and your time constant is L over R, and please recall the time constant for a capacitor is RC. If an inductor is connected to an EMF source for a long period of time where T is greater than 10 tau, it has zero resistance to current flow. That's going to be the situation when the switch is connected to point B, and we have current flowing like that. In addition, the current is at a maximum and is constant. The electric potential difference across it is 0. When it is disconnected from the EMF, which we do by moving the switch to point A, it's a make before break switch, then the current will decrease exponentially as shown in this equation and this graph until it hits 0. Start with the capacitor with charge Q in a series circuit with an inductor and an open switch. That's an LC circuit. The energy of the circuit is stored within the electric field of the capacitor. Close the switch. Initially, the current is 0 as the inductor's back EMF acts to oppose the current flow. It then increases as the capacitor discharges. The electric field and the energy in the capacitor is decreasing as the magnetic field and the energy increases in the inductor. The current first flows counterclockwise, then clockwise, and oscillates, assuming no resistive heating losses, with an angular frequency omega. The total energy remains constant and moves between storage in the magnetic field of the inductor and the electric field in the capacitor. The behavior of the LC circuit is analogous to the simple harmonic motion of the mass spring system. RLC circuit discharge. Here you have a capacitor, an inductor, and a resistor. You throw the switch to B, which cuts out the source of EMF. So this behavior resembles an RL circuit, but the resistor will cause the oscillations of the magnetic and electric fields to decrease to 0 after some time. The charge on the capacitor will also oscillate as shown as it is discharging. You have a sine-cosine function, which you can see there, but it's overlaid by an exponential decay curve until eventually it gets to 0. So here's the equation, here's our cosine, and here's the exponential decay.